Hello everyone, hopefully you can see me well. My name is Javel Wilson. I am a candidate of the Masters of Science in Mechanical Engineering at the University of the District of Columbia. My research advisor is Dr. Kate L. Klein, and today it is a great pleasure that I bring you through some of the work surrounding my thesis entitled The Simulation and Testing of Novel Fluidic Nanochannels. So first, my outline. I'll briefly go through the introduction, my motivational questions, my methods, before touching on my results and discussions. Finally, I'll make some conclusion and tell you about the future direction of this project before giving some acknowledgements at the end. So the helium ion microscope is a unique piece of tool. It has the dual capability of not only imaging like a typical scanning electron microscope, but it also provides the ability to machine. It does have some unique capabilities when imaging in that the depth of field is 5 times better than the SEM. But as I said before, because of the non-negligible mass in that helium has some considerable amount of mass, it's able to machine or mill away material in certain substrates. As you can see here on the lower left section in silicon dioxide, we see a milling behavior taking place. However, in particular substrate classes like silicon, what happens is we have kind of this swelling phenomenon taking place. Gold is one such material that mills away as well. And here we managed to create a cool design exploiting this swelling phenomenon and creating our NIS logo. So we somewhat characterized the dosage or the dose of the helium ion that and the implication of what it causes in the substrate. So here we kind of have at a low dose 1 times 10 to the 18 ions per centimeter squared. We have the occurrence or the beginning of the occurrence of the cavity, but we see that as we double that dosage, we kind of have identified a sweet spot where we have a medium dose and we have some level of uniformity in the cavity being formed. So essentially, the helium ions are populated under the substrate surface, and we go ahead and open the ends with the focus ion beam. So, with that being said, these cavities being evident under the silicon material, we believe that these cavities have some level of fluidic conductivity or potential for fluidic conductivity. So our motivational questions become, can we exploit the swelling phenomenon observed in silicon substrate from helium ion irradiation to develop a novel technique of directly writing nanochannels for useful applications? And also, can we prove the fluidic conductivity of machine nanochannels and in some way characterize their fluidic capacity? So the ability to do this can lead to several applications, some of which are listed here. DNA or molecular sequencing for lab-on-chip health diagnostics, also some level of thermal management or energy application, as well as others. So um, in order to test the fluidic conductivity or do any testing of that sort, we had to fabricate what is known as a microfluidic test strips, which takes place in several steps, as you can see listed here. But the main takeaway is we basically etched this design into the silicon chip. So essentially what we have a primary loop containing inlet reservoirs that is isolated from a secondary loop containing outlet reservoir. And the only connection between these two independent loops is this nano channel that we have machined using the helium ion microscope. So, once we have that design down pat, we then go ahead and assemble the device, which is comprised of a few parts, as you can see here. One key thing to highlight is the 3D printed mold, which allows us to properly align the PDMS lid, which is what we use to enclose the device with the silicon chip, as once the PDMS and the silicon come in contact, because of surface activation, an immediate bond is formed, so alignment is of key. We also employed or intend to employ a proof of concept experiment, some of which we have dabbled in some earlier attempts, which I'll go into. But the two proof of concept methods that we're looking into is fluorescent imaging through the use of fluorescent dye and also ion current measurements. So, as I said before, some earlier testing that we did kind of our initial attempt of this process, where we had an ion current measurement set up and we tried to flow salt solution through the device. However, some issue occurred in which we had a bonding of PDMS and silicon chip proved non-trivial. The coring of the wells and needle insertion somewhat compromised the bonds as well as some other issues. But with our new improved test chip design, we managed to conquer or get rid of most of those issues, for the lack of a better term. And we also created a seal device. We proved conductivity through the nano channels, as you can see here, at a flow rate of 40 microliters per minute. And one noticeable observation is the presence of air bubbles in those channels. So because of the COVID pandemic, we and the restrictions that it caused as far as facilities and the use of laboratory spaces, we pivoted and thought that pursuing a DOE in order to maximize or find factor level combinations that maximize flow throughout the device would be a worthwhile pursuit. So some of the factors that we've identified affects the flow is liquid type, pressure, nanochannel diameter, nanochannel length. And basically what we did is we did a Taguchi L9 DOE and managed to reduce or normally 81 experiment to an optimized 9 experiment in order to choose the best combinations for this entire DOE right here. So COMSOL, once we got that information, we fed it into COMSOL, and we had some difficulty at the nanoscale, some things that we still need to work through, but COMSOL did provide us a few useful information. It confirmed that the flow velocity within the microchannel relative to the flow rate at the inlet remains relatively constant, evident from these blue planes here. The flow velocity also significantly increased when the fluid in the microchannels enter the machine nanochannel. The flow rate profile indicates the slowing near the boundaries or the extremities of the channel, and that's due to fluidic friction or shear. And we think that capturing volumetric flow rate, which we plan to do, would be a good performance indicator for as a measure of efficiency of how well fluid is coming across this channel. So some final conclusions. Well, fabricated a microfluidic test chip and assembly device. That's something that we did. We created a DOE of 9 COMSOL experiment to optimize experimental conditions to demonstrate flow through the nanochannels. And we created a functional COMSOL model with some area for improvement. And moving on to future works, we do want to use the DOE and COMSOL results to experiment to optimize flow efficiency across the microfluidic device once we can, get through some bottlenecks as well as a few more. One important one, which is really a future work, and that's something that we intend to do or really hope to do, is explore patterning kind of more non-linear or complex nanochannel geometries for more novel applications. So I'd like to give thanks to my funding support from the NSF CREST Award and the Department of Energy Award. Also the Center for Nanoscale Science and Technology, CNST User Facility at NIST, Dr. Andras Valdard, who's the Orion PI at NIST, and also my classmates who contributed, Teddy, Jana, Chance, James, and Iman.